Hello and welcome. This morning we're going to be hopefully interviewing Dr. Tejinder Singh, a professor at physics at the Department of Astronomy and Astrophysics at the Tata Institute of Fundamental Research in Mumbai, India. His website, as I've shown on the screen here, you can find a link to in the description right below. He has quite an impressive resume of video lectures and articles that he has written on theories of quantum gravity, space time, and unification of physics. Unification is the merger of quantum mechanics with general relativity, two theories that don't ordinarily mix well. So new approaches have been tried where they're trying to get general relativity to emerge as an emergent theory from quantum gravity. And hopefully I have my time zones correct. It says 9 o'clock p.m. is 10:30 a.m. here. I've sent him the link now again, and I'm hoping that he joins us soon. You can find a number of papers of his on archive by searching for his name. Some very interesting theories on division algebras and towards quantum gravity and unification. Um, so while we wait for Professor Singe to show up, I'm going to go ahead and play one of his video presentations that he's been kind enough to share. So we can give him some time to get his the link and everything figured out, and hopefully join us for a Q&A discussion. So the gist of I think what he was going to present today is in this video. So we'll just go ahead and start this and play it for everybody.
Gravitation and quantum theory as emergent phenomena. Quantum theory without classical time as a route to quantum gravity and unification. I would like to thank my collaborators without whose participation this research program would not have been possible. Space-time, vector bundles, fermions, dynamics. Our knowledge of physics. In the words of Edward Witten, if one wants to summarize our knowledge of physics in the briefest possible terms, there are really three fundamental observations. Space-time is a pseudo-Riemannian manifold M endowed with a metric tensor and governed by geometrical laws. Over M is a vector bundle X with a non-abelian gauge group G. Fermions are sections of S plus cross VR, some S minus cross VR bar. R and R bar are not isomorphic. Their failure to be isomorphic explains why the light fermions are light and presumably has its origins in a representation difference delta in some underlying theory. All of this must be supplemented with the understanding that the geometrical laws obeyed by the metric tensor, the gauge fields, and the fermions are to be interpreted in quantum mechanical terms. We would like to bring these three observations into a unified fold, and for that we move on to trace dynamics, octonions, and unification. What are the new ingredients for unification which we now present? Adler's pre-quantum theory of trace dynamics, which is a matrix-valued Lagrangian dynamics. Octonions as a non-commutative spacetime manifold instead of R4, the familiar four-dimensional Lorentzian spacetime manifold. Chomsky-Cohn's spectral action principle, Dirac operator instead of metric, and hence a new Lagrangian which is the trace of the square of the Dirac operator. Exceptional Lie groups for symmetry, in our case that will be E8 cross E8, and Clifford algebras made from octonionic maps for describing elementary particles. Evolution in terms of Cohn's time a new concept of time available only in a non commutative geometry and derived from the Tomita Takesaki theory. There is no change in energy scale vis a vis Witten's remarks, our knowledge of physics, and it is the same physics which is being presented in a different formalism, driven by the motto that fermions must be described on a spinor spacetime as opposed to on a Minkowski spacetime, as is done in quantum field theory. And when we do that, we gain additional insights about gravitation and about the standard model. Looked at in another way, the ingredients for unification are as follows. On the four-dimensional Minkowski spacetime, which is curved by gravitation, there live fermions and standard model gauge fields, the latter described by a vector bundle. We are saying, let us take the square root of this four-dimensional Minkowski spacetime in the same spirit in which we take the spirit of the square root of the Klein-Gordon equation to arrive at the Dirac equation, let us also take the square root of the Minkowski spacetime, and when we do that, we arrive at a spinor spacetime, also thought of as a twistor space described by complex numbers. We next replace complex numbers by quaternions and then subsequently by the octonions to arrive at a complex bioctonionic space in which we have a Lagrangian with a E8 cross E8 symmetry. On this space, the complex bioctonionic space, we have unification of gravitation, pre-gravitation, and the standard model gauge fields, as well as the fermions, all together described as a geometry. And in reality, at all energy scales, fermions live in this octonionic space. Their description on a Minkowski spacetime is only an approximation. When we move down by taking this square root, there is no change in energy scale. Just as when we take the square root of the Klein-Gordon equation, there is no change in energy scale involved. There's just a better description of fermions, and the same spirit is being applied to the space-time as well. From Newtonian dynamics to trace dynamics, we are familiar that the action principle for a free particle in Newtonian dynamics on absolute three-dimensional physical space is the kinetic energy integrated over absolute time. So this is the Lagrangian. Now, to go over to trace dynamics, we replace the real number dynamical variables Qi by matrix valued variables Qi bold. Now, the total action of the universe is the sum over all degrees of freedom of integral over a new time, which we call Cohn's time. The position variables had been replaced by matrix valued position variables. The mass has been replaced by a length scale, Lp square by L square in units of Planck length Lp. So the Lagrangian has now become a matrix valued polynomial, and to get a scalar, we take a trace. So this is essentially the velocity of the particle in trace dynamics, and we sum over all the degrees of freedom in the universe. What makes trace dynamics special is that it has a novel conserved charge not available in classical mechanics nor in quantum mechanics, and that is denoted by the symbol C tilde, sum over all bosonic degrees of freedom of the commutator QB minus sum over all the degrees of freedom, the anti-commutator QFPF over the fermionic degrees of freedom. This has the dimensions of action, and this conserved charge is what replaces the Heisenberg algebra of quantum theory, giving us a pre-quantum theory. As you can see, the individual commutators are not constants equal to IH bar, but their sum is conserved. So this is like alternative to the Heisenberg algebra in trace dynamics. From trace dynamics to quantum field theory as an emergent phenomenon. Assume that trace dynamics holds at some time resolution, say tau Planck, which essentially is any time resolution scale not yet accessed in laboratory. This trace dynamics is a Lorentz invariant matrix valued Lagrangian and equivalently Hamiltonian dynamics. We ask, what is the emergent dynamics at time resolutions poorer than the resolution scale tau Planck at which trace dynamics holds? So you are not observing the dynamics as finely, as precisely as in trace dynamics, but in a coarse grained sense, similar to how we would want to describe water as a fluid if we are not observing individual atomic motions of the water molecules. The techniques of statistical thermodynamics can be used to show that the novel charge just presented in the previous slide gets equipartition since the charge is conserved. Once it is equipartition, it means the individual commutators QB, PB, and the anticommutators QF, PF, all of them are constant in the coarse grained sense and they are equal to each other. Hence, that constant is identified with IH bar. In this sense, the Heisenberg algebra of quantum theory emerges from trace dynamics in a coarse grained approximation if the underlying theory is not being examined at the time resolution at which it has been proposed. The Heisenberg equations of motion, which are a consequence of averaging the Hamilton's equations of motion of trace dynamics,
These
these
Heisenberg
Heisenberg
equations
equations
of
of
motion
motion
and
and
quantum
quantum
field
field
theory
theory
emerged
emerge
from
from
trace
trace
dynamics.
dynamics at thermodynamic equilibrium. Away from equilibrium, if the Hamiltonian is originally not self-adjoint, which is how it is assumed to be, under certain
Certain
circumstances, when
circumstances,
sufficiently many degrees of
many
freedom
degrees.
get entangled with each other to form macroscopic systems, the quantum system moves away from thermodynamic equilibrium and the quantum to classical transition takes place, giving rise to the emergence of the classical world. Trace dynamics admits superquantum non-local correlations. As is well known, the CHSH inequality is a version of the Bell's theorem and Bell's inequalities in which the non-local correlations lie between the range 0 to 4. Popescu and Rohrlich showed in a very important paper that if one assumes relativistic causality and non-locality, the resulting upper bound on the Bell type correlations is stronger than the bound permitted by quantum non-local correlations. The quantum bound is known as the Sirelson bound and lies between 2 and 2 root 2. The correlation, if it is classical, namely due to hidden variables, is less than 2, it is between 0 and 2. Classical correlations are between 0 and 2. Quantum non-local correlations are between 2 and 2 square root 2. And then there is this very surprising region, namely relativistic non relativistic causality implies or permits non-local correlations stronger than those of quantum theory, raising a question: is there a relativistically causal theory more general than quantum theory? And recently in this paper, we answered this question in the affirmative that trace dynamics, so long as the novel charge is not equipartition, trace dynamics can admit superquantum correlations, hence explaining why the PR bound is higher than the Sirelson bound. It is as if the Sirelson bound is an attractor at thermodynamic equilibrium. Uh, Quantum systems also tend to the Sirelson bound, and when the novel charge is equipartition, we know that thermodynamic equilibrium is recovered, and then the PR bound comes down back to 2 square root 2. This result suggests that quantum mechanics is approximate and not exact, and is in fact an emergent approximation to trace dynamics. Okay, we have the dynamics. Now we want to choose the Lagrangian for the unified theory. In this, we are aided very elegantly by the Chomsky-Cohn spectral action principle. It is known from the spectral action principle that the Einstein-Hilbert action of general relativity in a so-called regularized heat kernel expansion can be expressed in terms of the Dirac operator on the Riemannian manifold, namely, given a curved Riemannian geometry, write down the conventional Dirac operator on this curved spacetime. Take the trace of Lp squared d squared, where Lp is the Planck length. This quantity in a heat kernel expansion is equal to the Einstein-Hilbert action, which hence can also be written as the sum of the squares of the eigenvalues of the Dirac operator on the manifold, because that's what the trace is doing. This tells us, as was shown in an important paper by Landi and Rovelli, that the eigenvalues of the Dirac operator on a manifold can also act as dynamical variables instead of general relativity, instead of the metric of general relativity. So instead of using the metric as a dynamical variable, we use the eigenvalues of the Dirac operator as dynamical variables. And in order to, so this is a classical theory. To go from here to trace dynamics, we must raise the classical real number valued degrees of freedom to the status of matrices slash operators. That is what is done now to go to trace dynamics. Each eigenvalue is raised to an operator slash matrix lambda I hat, which is our new dynamical variable, the ith dynamical variable, in terms of which a configuration variable QBI is defined, whose Cohn's time is equal to lambda I hat. And which is this operator to which it has been raised? The very Dirac operator of which it was an eigenvalue. Hence, corresponding to the ith eigenvalue, we get a trace dynamics Lagrangian, which is integral over Cohn's time of trace QBI dot square. So this is the ith eigenvalue, which defines for us an ith atom of space-time. And if we sum over all the atoms, we have to do this sum by summing over all the space-time atoms. So there's a sigma I sum here outside. We have discovered the trace dynamics pre-quantum theory version of general relativity. How will the classical limit be recovered? Each eigenvalue operator, each lambda I hat operator will collapse to one of the eigenvalues lambda I, and then we can sum over all the classical eigenvalues once again to recover four-dimensional spacetime and Einstein-Hilbert action for general relativity. So the classical to pre-quantum transition is obtained by raising eigenvalues to dynamical variable operators, and the pre-quantum to classical transition is done by bringing by the spontaneous collapse of the operators to the classical eigenvalues. We can include matter now in the theory in the following sense. So this is, we are getting to our fundamental Lagrangian, which describes the unified theory. This part, QB dot dagger, QB dot is the gravitational part, to which we add the the fermionic part described by operators q dot f dagger and q dot f. These will play the role of right-handed fermions in the theory, and L is a length scale associated with this atom of space-time matter. There are only three fundamental constants in the theory: Planck constant, Planck time, and Planck length. In terms of these three constants, every other constant, dimensional as well as dimensionless, has to be derived from the theory without any fine tuning and without any further input from outside. Beta 1 and beta 2 are two constant unequal Grassmann numbers needed to make this Lagrangian bosonic. The matrices QB and QF are made of Grassmann numbers as entries. QB, the bosonic matrices, are made up of even grade Grassmann numbers, and the fermionic matrices are made up of odd grade Grassmann numbers. In this Lagrangian for space-time matter, which has only dotted variables, we
Hello, I'm here with Dr. I'm sorry, how do I pronounce your name?
Tejinder?
Tejinder Singh?
Yeah, yeah, Tejinder Singh. Yeah.
Singh. Okay, the H is silent. So, all right. I am honored to have you here with us. This is remarkable because I've had a number of people tell me that they can get relativity to emerge from quantum mechanics by separating the odd and even variables and using these non-commutative algebras. And I'm hearing the same exact thing as what you did here. You separated the odd and even terms into each side of this. Is that
Mm-hmm. Yeah.
Yes, this is great. Would you rather me just continue to play your lecture and then open it up to Q&A at the end, or did you want to take over from here? Or I wanted to give you the option of if you had
Yeah,
any.
maybe it's better if I communicate because I have the same set of slides. I could give a more talkative overview,
Yeah,
uh, and or if there are already some questions at this point, I can take them. Otherwise, I could set up the story, and you can stop me whenever you want and ask a question, or I can take question. Maybe if we talk, I feel that might be better.
right. I wanted to get my friend on here. He seems very knowledgeable about a lot of this stuff, and I hope others
Who's
will.
this church, is it?
This guy has a channel called Void is Yin Yang, and he goes into a lot of interesting stuff as well.
Yeah, yeah,
Then
yeah.
I had another friend who came up with another theory based on the work of Fabergé and Sedgwick, and this guy Daniel Kaufman, mathematician. He's
Mm-hmm.
into knot theory, and he has a lot of interesting theories on topological based theories of quantum mechanics. And again, it deals with these non-commutative algebras and the separation of the parts into the negative and the positives. And oh, here he is, right here.
Sorry.
Mm-hmm.
So, what do you think of this presentation so far?
Oh, me?
Yeah, you.
Okay. I just want to say it's a great honor, Dr. Singh.
Yeah,
Oh,
nice to meet you, sir. Yeah.
sorry, I have family in the background, so there might be. Okay, so I wanted to ask you if you could talk about the foundation based on Alain Cohn, or how do you pronounce Alain Cohn's last name? The Cohn time that
Alan,
you mentioned.
yeah,
Yeah,
Alan Cohn.
right. Could you talk about how he uses the triple spectral in terms of frequency? So if it's non-local, is he using a negative frequency as a frequency of light? A spectral. Would that be like a virtual photon then?
I mean, I don't use the full works of Alain Cohn. I used in particular the spectral action principle, which
Yeah.
relates the general theory of relativity to the Dirac operator on a given manifold. Maybe I'll start from the beginning, give you a background of
Yeah.
how I landed up with Alain Cohn. Yeah,
Awesome.
would that be okay? Yeah.
Yeah. Okay.
So I let me start by making a case why gravity is emergent and why it should not be quantized. We should not quantize classical gravity, and the reasons are the following. That is the sense from which I began 20 years ago, and now things seem to be looking good. The point is that if we look at how we practice quantum theory, it uses an external classical time. When we write down the laws of quantum mechanics, there has to be something to describe time evolution. And the time parameter is classical. It's not an operator, it's not a matrix, it's not quantized. And that is a part of the classical world. It's a part of a classical space time. Now, classical space times are produced by classical macroscopic objects by the laws of general relativity. Classical spacetime, classical objects like stars, galaxies all go together. Now consider the thought experiment, even in today's low energy universe, even in this room, that suppose everything was in a superposition of, let's say, two places. The table is in two places, the atoms are all in two places, the galaxies are in a superposition. Such a thought experiment is perfectly well legitimate even at low energies. In such a situation, we will not have a classical space-time geometry because matter is in quantum superpositions. So all the gravitational fields, all the space-time points also become in a superposition, and we are no longer left with a classical time. In a world in which everything is quantum and microscopic and superposed, we don't have a classical time, and yet we should be able to describe dynamics. This is my fundamental starting point. There should be a description of quantum theory which does not depend on classical time. How to find a way to describe quantum field theory and all quantum phenomena without making any reference to a classical entity like time or classical space-time. This is how I develop our approach to quantum gravity and unification, by looking for a way to reformulate quantum theory so that it doesn't have any classical time in it. So if I would be happy to take any questions at this point, or otherwise after that I can go on to say how I build the theory on this principle.
Well, I'm going to continue on with the lecture that we have put together. This is it right here, gravitation. So this is the one you'd put together and sent me, and there's a lot of good material in here. So I'm just going to continue off from this and let anyone interject with questions.
I tried to get to this point. So I've now laid the foundation. So let's ask ourselves this question. Even in a low energy universe like ours, there is a need to describe quantum systems without using classical time or classical space-time. How can we do that? So there could be various ideas. The simplest and the one that seems to work is to take note that we describe our space-time manifold using four real numbers. That is our classical space-time manifold, we would like to stick to similar number systems which are known as division algebras, ones which allow the operations of addition, subtraction, multiplication, and division. These are called division algebras, and there are only four of them. The real numbers that we are familiar with, the complex numbers, which are very prevalent in quantum mechanics, and then there are only two more division algebras, the quaternions and the octonions. We explore what would our description of dynamics look like if we use quaternions and octonions instead of real numbers to label space-time. There is another way to motivate it, that when we write the Dirac equation by taking the square root of the Klein-Gordon equation, we arrive at a beautiful Dirac equation for electrons described as spinors. But we did not at that time, for example, take the square root of space-time. You know, matter and space-time should go together. When we go to fermions, we should take a square root of, we consider taking a square root of Minkowski of space-time, and it turns out that the correct mathematical way to describe the square root of a Minkowski space-time is precisely to use quaternions. So we would now like to describe elementary particles such as quarks and leptons, electrons, neutrinos, not on a space-time made of real numbers, but on a space-time labeled by quaternions and preferably the octonions. Octonions are eight-dimensional non-commuting numbers which lay the basis for this new formulation of quantum theory without classical time. Because it is a non-commutative, any questions? So my space-time is now eight octonionic dimensions or 10 space-time dimensions. 8 octonionic dimensions are equivalent to 10 space-time dimensions. So we are in a higher dimensional space-time. We'll come back to what to do with the extra dimensions. So we are going to now reformulate all the dynamics as if each particle is carrying an octonionic space-time with it. And I call such an entity an atom of space-time matter, which was introduced in this talk. An atom of space-time matter, or in short, what I call an ion, is an elementary particle like an electron with all the fields that it produces. Electron, along with its gravitational field, its weak force, and its electromagnetic field, forms what I call an atom of space-time matter, which is living in this octonionic space. Because we are now in a non-commutative geometry, namely the geometry provided by the octonions is non-commutative because these directions don't commute with each other, we are in the domain of a geometry essentially close to Alain Cohn's non-commutative geometry, which has a subtle property that it brings in a new parameter which plays the role of time as a classical order parameter, which is what I call Cohn's time. So along with the octonionic space-time manifold, we have an additional time parameter, which is the one that flows. Cohn's time is the time that flows. The time coordinate on a space-time manifold is just a coordinate. It doesn't flow. It has the same status as the position coordinates x, y, z, and t. These are passive. This time is not flowing. Cohn's time is the one that's flowing. And at different values of Cohn's time, I will examine the octonionic space-time. So we have now a new coordinate system. We have a new time parameter. We have got rid of the classical time of space-time. So thankfully, we will not use that to measure the evolution. That in fact becomes an operator, just like position. But because we are in a non-commutative geometry domain, we are blessed with a new time. Yeah, that's Alain. We are blessed with a time parameter that he explained to us. So, okay, so we will describe elementary particles on an octonionic space as evolving in Cohn's time. What do we need next? We need a law of dynamics and we need an action principle, and then we are ready to go. Again, I would take a break if there are any questions or comments at this stage.
It's no, it's flowing perfectly. Thank you.
Yeah, this is
Okay.
great. It's connecting a lot of these dots for me that I need to now go fill in all
Yeah,
this.
perfect. Yeah, the slides you're showing are perfect. Okay, so let's go on. I need now a law of dynamics which gels well with these non-commuting coordinates. And we cannot have quantum theory because quantum theory assumed a classical time, a classical space-time that is gone. So we cannot do quantum theory on this octonionic space. We must come up with something new. And there we appeal to Stephen Adler's theory of trace dynamics, which I'll try to motivate in a few words. In my opinion, it's very beautiful. Quantum theory, as we know it, emerges from Adler's trace dynamics. So gravity and quantum theory both are emergent phenomena. I think you should look for Adler's trace dynamics, Stephen Adler trace dynamics. Yeah,
Adler.
ADLER, yes. Oh, Samaya, the first one is my paper, but you can go to Stephen Adler trace dynamics. Just little down. Go back. Yeah, this one. Stephen, the one above that. The one above that. Yeah. This would probably tell us something. Okay, so let us go back to Newton. Let us remember Newton is doing classical mechanics with point particles. Hamilton, Lagrange, and many others then made Newton's mechanics more formal. It comes from an action principle, it has a Lagrangian, it has Hamilton's equations of motion. But it is all classical, and the degrees of freedom, the Q's and P's, are point particles described by real numbers. For space-time, we have exchanged real numbers for octonions. What about the dynamics? Let's ask this question. Suppose Newton was to do classical dynamics with matrices. Instead of with real numbers, he will do classical dynamics with matrices. That, in a sense, is trace dynamics. That I will repeat Newton's prescription, Hamilton's Lagrange prescription, but my dynamical variables are like those in quantum theory. They are matrices, they are operators, but I will not do quantum theory with it. I will not impose the Heisenberg algebra QP commutator equals IH bar. Instead, we will repeat Newton's mechanics with matrices. But is that trivial? No, it turns out it is not trivial. If I just write a Lagrangian mechanics with matrices, it admits a new conserved charge, which is not there if you're working with real numbers. And that conserved charge is known as Adler's conserved charge because he and his student Andrew Millard found it. It is very beautiful. Take the QP commutator for any degree of freedom. Q is now a matrix. P is a matrix. Take the commutator QP minus PQ. This is non-zero even in trace dynamics. So this matrix dynamics with Newton's matrix dynamics Newton's Lagrangian dynamics with matrices, what is called trace dynamics. In this theory, like I said, there's a beautiful conserved charge. Because Q's and P's are now matrices evolving with time, the commutator QP minus PQ is not constant. It evolves with time. Unlike quantum theory where QP minus PQ is IH bar. Here is not IH bar, it is changing with time. But if you take the QP commutator for the first degree of freedom, add it to the QP commutator for the second degree of freedom, and so on and so forth, the sum of the QP commutators for all degrees of freedom, that is a constant. That doesn't change with time. Here you see a hint of quantum theory. When you go to matrices from real numbers and continue to do Newton's dynamics, you are no longer doing classical dynamics. You are doing something which is equivalent to a pre-quantum theory. The very act of using matrices instead of real numbers in Newtonian dynamics takes us to a stage more general than quantum theory, which is pre-quantum. So Adler's trace dynamics is a pre-quantum theory because it has this beautiful conserved charge. Sum of QP commutators over all degrees of freedom is a constant in time. Let us assume that this dynamics takes place at some very high energies beyond what has been observed led by the LHC, say beyond TeV energies. Because below TeV energies, quantum theory and classical mechanics work beautifully well. So we go beyond the TeV energies. Let's assume that Adler's trace dynamics holds there. Then Adler asked this question: suppose I am not observing at that high energies, I'm observing the dynamics at lower energies than where trace dynamics is valid. Trace dynamics is valid at some very high energies. I'm observing at much lower energies. What does this coarse grained dynamics look like? It's like saying if instead of water molecules, I'm observing macroscopic properties of water, it looks very different from the motion of individual molecular motion of individual water molecules. In the same sense, trace dynamics, when it's observed at lower energies, something again very interesting happens. The conserved Adler charge gets equipartition over all degrees of freedom. So the QP commutator for all degrees of freedom upon averaging become equal to each other. The sum was a constant, each of them on average now becomes equal at low energies because of thermodynamic averaging. And once they are all equal, I can set them equal to IH bar. The Heisenberg algebra of quantum theory emerges from trace dynamics at lower energies after coarse graining the microscopic degrees of freedom. So in this sense, quantum theory is an emergent phenomenon, emergent from trace dynamics, and we will work with trace dynamics on the octonionic space. So what have we done? We have started with Newtonian dynamics, replaced real numbers by octonions to form a new space-time manifold, replaced quantum theory by trace dynamics, and work with matrices instead of Newton's real number. So Newton is doing three-dimensional space, absolute time, real number degrees of freedom for matter. We replace real numbers by matrices. We replace space-time manifold by octonions, and we replace the dynamics by Adler's trace dynamics, and we have a certain simple action principle for it. We are all set now. So we have a new coordinate system. We have a new Lagrange. Yeah, please. Yeah.
I was just watching at double speed on YouTube to catch up. Okay, so this is very interesting. So you these trace dynamics, these are a higher energy theory that
emerges from quantum mechanics at that?
Okay, I should be quite careful. What is really what is at play is not energy, though there is a connection. You were there when we talked of Cohn's time, right?
Hmm.
So Cohn's time is keeping track of evolution. Suppose this evolution has an intrinsic time scale which is of the order of Planck time. For example, some time scale higher than what we have probed so far. Okay. And let us say trace dynamics holds at a time resolution some tau critical which we have not yet observed. I'm going to coarse grain over time intervals that are much larger than tau critical. So it's not from high energy to low energy. It is from fine grained Cohn's time resolution to coarse grained Cohn's time resolution.
Well,
So a
but
new
that would imply a frequency and therefore an energy scale, wouldn't it?
so in that sense the connection is there, but it is indirect. So let me try to be a little bit more careful there. So if so let's scale tau by tau Planck. We have a dimensional quantity. Let us multiply that by h bar, and let us try to create something like an uncertainty relation, h bar tau by tau Planck. So
Right.
I want to stay out of energy in the tau by tau Planck is just a dimensionless measure of Cohn's time. H is a measure of action. If all degrees of freedom of interest have action of the order h bar, that is quantum in nature. So that is the action has become small. Now I can make tau by tau Planck large. If we coarse grain over time intervals much larger than tau Planck, we will get quantum theory from trace dynamics, but there is no direct energy scale involved. What we are comparing is the actions of systems and the tau times. Let's go over it again. If I've confused you, let me come to it in a different way. When will we call a system quantum gravitational? Normally, we think of a system as being quantum gravitational when the energy scale is the Planck scale. Now, I'm going to disagree with that. I'm saying that's a special case. A system is quantum gravitational when all degrees of freedom have actions of the order h bar. Now, we would call such a system quantum. I would say it's also quantum gravitational because I don't have a classical space-time. When all degrees of freedom are quantum, we argued that there cannot be a classical space-time manifold because quantum systems are in superposition. They cannot produce a classical space-time. So this I call a quantum gravitational situation, which can be at low energies. If along with actions being order h bar, length scales are order Planck length and Planck time, then it becomes a Planck energy quantum gravitational system. We can have Planck energy quantum gravitational systems. We can have low energy quantum gravitational systems. Low energy quantum gravitational systems are those which are not being probed at Planck length and Planck time scales, but have actions of the order h bar.
Okay.
So now let's try to go back to trace dynamics because I want to try to answer your question in a satisfactory way and try to make it clear why energy is not the thing at stake, but time resolution of tau with respect to tau Planck is at stake. And the
Well,
conjugate variable to that is not energy. The
so
conjugate variable to that is action.
if I could elaborate in my own research, I'm approaching this from a slightly different angle, perhaps, but I think that
Yeah,
the
yeah.
direction we're going is the same. So I'm viewing this as a as you go higher energy scales, shorter time length, they're similar, but um, what I'm attempting to do is derive the weak force and then the strong force as nonlinearities introduced to electromagnetism, um, because at that size scale, I mean, I'm kind of going at it from a material science perspective, but you can imagine that if you have some virtual particle pair that um, that it comes into existence on a certain time scale. If you add enough energy to that space, now these virtual particle pairs begin to overlap. And just like a transition from a gas to a liquid, now you have a phase transition where you've gained the weak force and the strong force potentially at those side scales. So that's kind of the approach I'm taking, and I'm curious to see where it's
So
similar.
let's do one thing. Will try to come to a point where to say for me where the weak and strong force come from, and then let's compare with what you just told me. Is that okay?
Sure.
Yeah. So okay, now I realize how to answer your question about what is the conjugate variable to this tau constant, why it's not energy.
Yeah.
Now it becomes clear. I just a sidetrack. The Adler conserved charge, it's normally indicated C tilde. It might be there one. The conserved charge C tilde is the quantity that is conjugate to tau over tau Planck. C tilde has dimensions of action. It's a QP commutator, so it has dimensions of action.
If you have a slide that you do you have a slide you could bring up on your screen? You can share your screen, by the way. There's a button at the bottom.
Yeah. Let's do that. Let's see the expression for.
I'm having trouble up with slides for you. I don't know the papers as well as you, and I'd like to bring up
right.
an example.
So
of what you're talking about on the screen.
Now I
I'll
share the screen. Share screen. Please. So somewhere there's a slide here. Maybe this one. No. Not share screen, present slides.
The other two things I'm curious about. I had two other questions as well.
It says present with a plus inside the screen.
Yeah.
So
sorry.
The other two questions I was curious about is how does this relate to Wheeler-Feynman absorber theory? Because they tried to have a quantum definition of time that was different from the classical large scale.
Could you say their name, please, again?
Wheeler-Feynman absorber theory. John Archibald Wheeler.
Okay. I'm not too knowledgeable about their work, but I'll come to it. Sorry, we'll come back to the slides in a moment, but just to complete the answer to Michael's very important question, the conjugate variable to Cohn's time over tau Planck is the Adler charge. When the Adler charge is not equipartitioned, its spread is very large. It's spread away from the mean value. The RMS spread is very large, and tau is of the order tau Planck. At Planck time resolution, the Adler-Miller charge spread is too far from equipartition. So the spread is small. No, the spread is large, and tau by tau Planck is small. This is the deep trace dynamics regime. As we increase tau over tau Planck, namely reduce our resolution, the Adler charge gets equipartition. Its RMS spread goes to 0. So the Adler charge spread is becoming small, tau over tau Planck is large. So now I can answer your question better. At poor coarse graining, when we are not observing the system at Planck times kind of scale, the Adler charge is equipartition. There is this kind of a conjugacy relation. So we have one more uncertainty principle. position momentum uncertainty principle, time energy uncertainty. This is for the time coordinate. The time coordinate is having a correspondence with energy, but Cohn's time is having a correspondence with the Adler charge. So if you don't observe at tau Planck resolution, you will have a equipartitioning of the Adler charge, and you will get quantum theory. So
I'm curious as well. This Adler charge, it does. Is this analogous in any way to quantum squeezing? Because it reminds me a lot of it.
You could really, yeah, that's a good point. We could think of it like that. The classical limit is being arrived at by, spreading it in a more home. So yeah, it is like you could compare it with
quantum
squeezing.
You're moving around that Adler charge into. You could think of it as moving around that Adler charge. It's still IH bar on average, but with quantum squeezing, you are taking some quadratures and you're making them more or less uncertain, but the total amount is conserved still.
Yes, I agree with you. There is a parallel. So
can I make a?
Yeah, I'll just one last attempt to share the screen.
I was just going to interject that maybe it's more like a Poisson bracket in terms of the mathematics.
Oh.
Like because he's talking about matrices. So,
gotcha. I'm still learning this stuff. It's a big lift.
We are honored to have you as our professor here today.
Yes, thank you, Professor.
Yeah. So okay. So are we getting close to completing the story? We have a new coordinate system which is non-commutative. We have Cohn's time. We have Adler's trace dynamics. We have a nice action principle, which is quite simple. With the claim is that this captures all of standard model and gravity, and it is what we need to practice quantum theory without classical time. And now it turns out the big surprise is when your coordinate system is made of octonions, amazing new things begin to happen. This is actually the work of other people, which I have used or tried to build on. And that is what takes us to particle physics and unification. So should I go on?
Well, I was just about to ask that as well. Like, this must have some interesting implications for nuclear matter calculations.
Right,
sure.
right. So let's get there. Somehow I'm not able to share my screen. My ignorance. I should know how to do it, but it's okay. We can come.
Are you on a Mac?
I'm on a Mac. Yes.
Yeah, that's why you have to go into your settings and then allow your Chrome, whatever you're using, Google Chrome, to access your screen and give it access to a screen share.
Okay.
In your settings.
Google Chrome. Okay. Yes.
Have you ever read this book? They have a copy of this down the street at Brown University. I'm here in Rhode Island, so I might go take out a copy of Stephen Adler's book. Quantum Theory is an Emergent phenomenon. The statistical mechanics of matrix models as the precursor of quantum field theory. So this is a deeper. He must have. He'll be back.
When he's talking about this as pre-space,
yeah.
So this is similar to what Basil J. Hiley also does with the Bohmian. He's
spell that and look it up. So
Basil. Oh, like if you just search Basil Hiley pre-space, you'll probably get something. It's I'm sorry, I'm using the British pronunciation. It's Basil. That's like my
BASAL.
I'm sorry, Basil. BASIL. Or no, yeah, that should be right. Yeah, and then Hiley is HILEY. Jack Sarfati was mentioning Basil-Hiley. Yeah.
Here's
There we
that.
go. I think he's
Yeah, yeah.
sharing the screen.
Yeah.
I'm gonna mute.
Yeah, so-
See, yeah, he might have had to leave to. You might have to exit out of Chrome.
I was thrown out to allow me to share the screen.
Yeah, I've done that too in the past.
Yeah, no worries. We're still here, man. We're not giving up just yet.
So
Click
do
your
we see anything? Do we see the screen?
Yeah,
StreamYard is
yeah.
sharing.
Let me share your screen right now. All right, there. All right, we got your screen shared. You just gotta click off of the StreamYard link, and it will take us out of the Warp portal.
What should I do?
You have to click on the other window that you wish to share with us, because we can see your screen now, but all we're seeing StreamYard, so it's putting us in the Warp portal. So as soon as you click on something else, we'll be seeing that. So just be careful. If you have anything sensitive open, close it right now so you don't have.
Yeah. There's
they show
nothing
that.
there.
Yeah.
So share screen. I should get my slides on first. Yeah.
Yeah, get your slides ready, and so that you can I think choose to share a specific window or.
So the slides are on now. What should I do?
And then go back. You have to go back and reshare your screen with the present button. The present button. So he worked with David Bohm. So this is like Bohmian mechanics, and this is where I think a lot of quantum mechanics went wrong with the Copenhagen interpretation.
Yeah, the cone, but Basil-Hiley relies on Alain also cone. He's working on a new paper based on Alain Cohn also. I just sent him this. Alain Cohn did this lecture to physicists, and maybe Dr. Singh was at that lecture. Did you? Oh, he can answer that. But anyway, yeah, he gets into entropy, and it's really fascinating because he's basically saying that entropy originates from the inner cross products of the matrices, which is what this Jordan, you're adding the non-commutative inner cross products of the matrices, and so that's what makes it non-commutative. And this is what this Dr. Singh is referring to with his new space-time matter atom being non-commutative, so that it's able to flow in time before you have a classical time created. And so it's yeah.
Sorry. Go ahead, please.
Well, I'm just saying it's non-local and it's also entangled. And would you relate this at all to Roger Penrose's concept of proto-consciousness?
Yeah, I haven't thought about it. Maybe I could say, Jeremy, I could send my slides to you, and
yes,
you could share.
Yeah, you can just say it next.
That would be easier.
I will certainly handle it.
I like your answer. I haven't thought about it. That's a good answer. That's the right answer.
I mean, yeah, it's good to like cross-pollinate ideas a bit, and that's helpful. Actually, I would be curious, Professor Singh, what you would think of. There was a fellow, Jack Sarfati, kind of controversial, but he did an excellent presentation recently on Tim Ventura's channel. At least
I've followed Sarfati in the past, but not of late.
Right.
So Jeremy, I emailed you the slides. We can share it. So let's get back to the octonions. The octonions now provide a coordinate system similar in spirit to the Minkowski's flat space-time, which we build general relativity and quantum theory on, but it is non-commutative, non-associative, and that brings in extra constraints. when we try to define elementary particle states using spinors made on this octonionic spacetime, we are in for a surprise. We find that we can only get standard model quarks and leptons. The charge is quantized as observed, 0 for the neutrino, 1/3 for the down quark, 2/3 for the up quark, and 1 for the electron. We find that there are 3 fermion generations. We find that there is all this is a consequence of the symmetry groups of the octonion, starting with E8 cross E8 and their subgroups. And we find a right-handed counterpart of the standard model, which can be identified with pre-gravitation, from which normal general relativity emerges, but a generalization of general relativity also emerges. And lastly, the standard model parameters like fine structure constant, mass ratios, Weinberg angle, the CKM matrix for quark mixing, these are no longer free. The action principle of the theory, along with the properties, the algebraic properties of the octonions, fix the free parameters of the standard model. And for me, this is the biggest plus of this theory, that we understand where the standard model of particle physics with its SU3 color cross SU2Y cross U1, SU2L cross U1Y, where does it come from? It comes from the geometry of the octonions coupled to a trace dynamics theory. This is and there is a right-handed extension, which is like pre-quantum theory, pre-gravitation. One can take a classical limit of this theory, and in that limit, general relativity emerges. And once you have a classical spacetime, quantum theory, as we know it, also emerges from trace dynamics. So from this underlying octonionic theory framework, we can recover quantum theory and gravitation. Jeremy, something has happened in the transit. Maybe is it possible to play the talk itself? We will stop at various. Let's play the talk. Yeah, this is better, I think.
Yeah, that looks good.
That looks good. Yeah. Let's stop here. Yeah. So here we have the Adler charge. If you go up a little bit, maybe. Right. So this is the equipartitioning of the Adler charge. If you go one slide up further, if you go, this is the Adler charge. The symbol C tilde. This is the new conserved charge which arises if we repeated Newtonian dynamics with matrices instead of real numbers. We go to a pre-quantum theory, which is that the sum of the commutator minus the sum of the anti-commutator for fermions. Sum it up for bosons, subtract it for fermions, and this object is conserved, and at lower resolution than Planck cones time, it is equipartition. We can go to the next slide. It gets equipartition. We can go to slide 6. You can go to slide 6, please. Right. So this is the equipartitioning of the Adler charge if we are observing a time resolution poorer than Planck time. Right. Yeah. So, and then if we go down, you will see that the theory, if you like, we can talk about this. If you want to talk about Bell's inequalities and non-locality, it turns out that
for sure.
Yeah, let's talk about.
Can I?
The condition.
I'm sorry.
Ask. Go ahead.
Okay. When you bring up the the thermodynamics, would that involve storing information like? Because Nobel physicist Gerard de Hooft, he has this idea of a virtual black hole at the microscopic
Yes,
level that would be able to
yes,
store information. And so is your
yes,
space-time atom similar to that?
yes, yes. When we do the coarse graining and not observe at tau Planck resolution, we are losing information. Because we are not observing at the fine grained scale, we are losing information, hence we are gaining entropy. So the black hole entropy in this theory really emerges as a consequence of not observing the atoms of space-time matter too finely. In fact, I have a proof
Yeah,
for that. The black hole entropy results from coming down from the Adler time resolution.
thank you. That's fascinating.
Yeah.
So
Okay.
I saw this in the presentation earlier, but I didn't understand these. So you have Bell's inequality, and what's the root two and the 4 mean here? What are
Yeah,
these?
so let's go to that. Jeremy, could you kindly get it? Yes, yes. Now, we understand Bell's inequalities as allowing non-local correlations stronger than would be permitted by classical theories, which are hidden variable theories. So, a particular implementation of Bell's inequalities is something known as the CHSH inequality, specific to a particular setup with Alice and Bob and Alice apparatus and a Bob apparatus, which gives you a very simple quantitative picture of the Bell non-local correlations. Jeremy, could we kindly go back to my slide, please? Right. So, classical systems would allow a correlation of at most 2 in the CHSH inequality measure. Quantum systems allow that to go up to 2 root 2. That is the Cyrilson bound. Quantum non-local correlations are stronger than the classical value of 2, but they cannot be stronger than 2 root 2. Naively, one would have thought those are the strongest non-local correlations possible. But these gentlemen, Popescu and Rohrlich, a couple of decades back, asked this important question. Suppose we only impose the condition of causality, no faster than light signaling, relativistic causality. How strong is the allowed non-local correlation? Is it as strong as quantum theory or stronger? And that was the surprise. It can be as strong as 4. The condition of causality allows non-local correlations stronger than those permitted by quantum theory. Now we have a deep question in front of us. What is happening between 2 root 2 and 4? It's not quantum, it's called supra-quantum. Does nature permit it? Or is there a theory more general than quantum theory which permits it? Experiments have never seen it, but that doesn't mean they will never see it. Maybe they'll be seen at higher energies.
I see. So this is a
So,
motivation for finding some generalization that includes quantum mechanics.
yes, the good thing is that the generalization is already there. It's Adler's trace dynamics. Recently, we showed, along with my student Rabsan Ahmed, it was really his smart discovery, that Adler's trace dynamics, so long as the Adler charge is not equipartitioned, allows non-local correlation stronger than 2 root 2, thus explaining why the Popescu bound is higher than the quantum bound. Adler's theory is more general. It holds when the Cohn's time resolution is of the order Planck time. So when you go to higher fine-grained Cohn's time resolutions, you start to see correlations stronger than quantum. It means if Alice and Bob were making measurements of the time of arrival, say, of the photons or the electrons in a pair, with a time resolution higher than, let's say, a TeV scale. Planck is just a reference point. any energy scale higher than what has been observed, say about a TeV, is a candidate for this critical rest scale, the Planck Cohen's time scale. So the
And
prediction is if we observe well correlations at very high energies, we will see this violation of the quantum bound. We will see this supraquantum correlation. And if we do that, we will establish that quantum theory is an approximate theory and trace dynamics is indeed more general. So this is a very important experiment to try. I'm talking to some people, maybe you have some new ideas how to do such an experiment.
I have some thoughts on that. Also, it's very interesting because Jack Sarfati's very most recent talk also mentioned something similar, that when you introduce these nonlinearities and behaviors, you get stronger non-local correlations, which is
Okay, great.
Dr. Singh, to bring this back to Cohn's time, along Cohn, he does state
Okay.
that his non-commutative time is more dense than the real number continuum.
Yeah, okay. At least in the language of octonions, that would be understandable. But I don't know whether he didn't probably have octonions in mind in particular. But any non-commutative number system would definitely have the Cohn's property of being more dense.
I'm also curious if you've read. There's a paper I read a while back that reminds me a lot of this stuff, or this stuff reminds me of that. And that book, that paper, it was called what was it? It is Quantum Mechanics: An Island in Theory Space. It made some interesting arguments about.
Yes.
It's a good paper.
I forget the author's name. It is essentially this issue of supraquantum correlations. Maybe Mueller, maybe someone else. Yes, not Mueller. Scott.
Scott
Yes,
Aaronson.
yes.
Yeah, very
Scott
good
Aaronson.
paper. Very good paper.
Yes. I don't know if he was talking of the Cyrilson bound or something else. I don't know. We can find out.
He was mentioning some properties of the L1 and L2 norm, I think, that made them physical versus. So they're higher norms, but you can't use them for the same sort of physics. Like the L1 norm corresponds to normal matter, and the L2 norm corresponds to quantum matter, something along those lines. It's been a while since I read it, and then none of the other norms are relevant or something.
Yeah.
But yeah,
I forget exactly what was there, but yes. So I do believe that one day we will discover these supraquantum correlations experimentally. It probably involves doing Bell's experiment with elementary particles at high energies beyond the TeV scale.
what about using squeeze states? Because you're essentially you have IH bar, but now your uncertainty is moved into one logic or another. That could be interesting.
Yes. I don't have experience with that, but I agree it's a good idea. You have to go into maybe this quantum non-demolition kind of situation where you beat the uncertainty principle. Yes.
Dr. Singh, could you talk about how you derive the discrete find constants charges? The Jordan.
Let's go to that. Let's go back to the slides. Yeah, maybe if we could look at the few particle physics slides and then come here. You could kindly go up a bit, please. One more. Right. So this we have done. Then we could go down to slide 8. So this is where we constructed the action principle for this so-called octonionic theory. This action principle is such that in the classical limit, it will give general relativity. And when a classical spacetime is present, it reveals the standard model action. It reveals the strong force, the weak force, and the electromagnetic force, all because of symmetry properties of the octonions. So now we can go down and see. Uh, Right. So that this is just a definition of the octonions, and the action basically is the Dirac operator on the octonionic space, the square of the Dirac operator. And yeah, maybe this the last equation on page 9 is interesting. What it is telling us is that these Q matrices, Adler's matrices, which are there in trace dynamics, they are playing the role of curving the octonionic space. The octonionic space is a non-commutative analog of flat Minkowski spacetime. Minkowski spacetime is curved by the metric, by general relativity. The octonionic space is curved by these matrices, and these now carry information not just about gravitation, but also about the standard model forces, strong, weak, and electromagnetic. By increasing the number of dimensions of the space-time and using these matrices to curve that space-time, we have unified gravity with the standard model. So this is in the sense of a Kaluza-Klein theory, but not using the metric, but rather using Adler's matrices.
So the non-commutativity is what allows it to be curved here, correct?
Yes. The
And
curvature
not
is
because we have some particle corresponding to graviton as derived like the other particles.
okay. So let's go to the next slide. I'll answer your question here. Slide 10, please.
So it's, I guess also,
Go
yeah.
ahead, go ahead.
How does it map to quantum fields and like? So do we describe this as a new field, or I mean, you mentioned it's not quantized, I think. So we'll go into it. Yeah.
No. This because this is Adler's trace dynamics, already pre-quantum. The Q's and the corresponding P's will not commute. So we are already in Adler's pre-quantum theory. We are doing Adler's theory with this specific Lagrangian, which describes gravity as well as the standard model forces, for the reason that the symmetry group of the octonion, the largest symmetry group we can associate, E8 or E8 cross E8 if it's a bioctonion, it has subgroups SU3, SU2, and U1. The symmetry group of the octonions have precisely the desired subgroups of the standard model if a particular branching is chosen, which I can show it to you in the next slide. So this particular, could we go to slide 11, please? This particular Lagrangian that we have constructed will be assumed to have a E8 cross E8 symmetry, which is reminiscent of the heterotic string theory of the 1980s, but now used in a different way. One E8 will be associated with left-handed fermions and the standard model. The other E8 will be associated with right-handed fermions and what I call the pre-gravitational sector, SU3 grav cross SU2R cross U1 grav. So this branching of E8 cross E8 shown here, SU3 color cross SU2L cross U1Y cross SU3 grav cross SU2R cross U1G, is our emergent theory. It has the standard model and it has gravitation, but more general than general relativity. SU2R is what corresponds to general relativity, but there are two new elements, SU3 grav and U1 grav, whose consequences we are still working to find out. All these forces are mediated by spin 1 gauge bosons. There is no spin 2 graviton except perhaps in an affective sense. The spin 2 graviton will have to be a composite of two spin 1 gauge bosons. So in this picture,
This is
three
even more.
graviton.
Sorry for interrupting again. I got excited. This is exactly what I've been saying about squeezed photons. So when you take two photons, you can create something called a squeezed vacuum state, and this squeezed vacuum state is it's a composite. It's essentially it's an entangled two photon state where your classical amplitudes all cancel, but you still have your variability in the uncertainty. That's exciting. That's exactly what I've.
Does it behave like a spin 2 state?
Yes. So I don't know exactly how to. I think it should. So you're taking an outer product when you have these photons. So that object could be spin 2, but I have to look at it more. I've had so many other projects going on. It shouldn't be a difficult calculation.
If the spin 2 graviton exists, it would be pretty much in the sense in which you are suggesting some kind of squeezed classical limit of these spin 1 gauge bosons. And yeah, there's a lot of more detail there. So
All
maybe
right, so
yeah,
I'm
we
going to
could go.
call the LIGO detector. Well, I guess
Yeah,
it's
we are
not
on the
radio.
same page. I have
Doctor,
never been comfortable with a spin 2 graviton. Why is gravity so different from other interactions? I don't understand that. Sorry, I will just put my laptop charger on. Give me a moment, please.
Well, thank you so much for going through this. Sorry for interrupting a couple times, but all these your answers will be extremely helpful towards getting us to a better understanding of this. Thank you.
Yeah, yeah, it's a pleasure to talk. Please feel free to interrupt. We could
I
go
have
back to the slide.
Dr. Singh. So when you like to relate this back to the squeezed states, basically the time frequency uncertainty, it originates from the non-commutativity. So when you're talking about those square root masses, you're talking about discrete numbers in the matrices.
Yes, in Planck units, the masses are in Planck mass units. That's where the ratios were found. Why the actual masses are so much smaller than Planck mass is a problem we will come to. That's really the hierarchy problem. Why the Higgs mass is so small on the Planck scale. That has not yet been addressed. We'll come to it, but I don't think that will be a impediment in progress.
All
These
right.
masses are discrete numbers in Planck mass units.
Thank you.
Okay. So before the symmetry breaking, before the E8 symmetry, cross E8 symmetry breaking into this branching which leads to the observed universe, before this symmetry breaking, we do not have separate notions of charge and mass. We have a unified quantum number, essentially electric charge times square root of mass. If all the forces have been unified, I should not be talking of charge and square root mass as separate entities. These also unify, and that becomes the source charge for the unified force. There is a unified force which is described by this weird. Yeah.
This is like similar to what Kurt Jamungal, I sent you that lecture with Sal Pays was talking with Stefan Alexander about the super force where they unify at this level.
Yeah. So we could call this the super force in their language, and its corresponding source charge is E times root m, electric charge times square root of mass.
Another analogy would be the Bryan-Josephson junction, of the Josephson effect, where he's the origin of charge, according to the National Institute of Standards for the volt, is due to the entanglement due to space-time symmetry breaking. But that actually originates from the non-commutativity, as you're pointing out. That's
Here too, electric charge originates as a result of symmetry breaking. Mass also originates as a result of symmetry breaking. This symmetry breaking is also a quantum to classical transition in which the ordinary four-dimensional space-time of our world emerges from the non-commutative unbroken phase. I hope you get the picture. Symmetry breaking separates standard model from gravitation.
Right.
Yeah.
And
Yes.
my conjecture is that that is the same as the electroweak symmetry breaking. A cosmic inflation ends at the electroweak symmetry breaking scale, separating standard model forces from gravitation and standard spacetime. Now
So
I go to
yeah.
answer this question about the origin of these constants, but please, your question first.
Well, is this going back to the photon? There's been a lot of models lately that the electron, spin, the one half spin of the electron is actually originates from a one half spin photon, or two of them combined together that are non-commutative.
This is a different idea from
Okay.
mine. My picture is that bosons are composite of fermions,
Yeah.
but the fermions are more fundamental. For
Oh,
me,
right,
I
right,
may
right.
be wrong. I may be wrong,
I
but the
agree.
fermions are more fundamental. Yeah, Michael agrees. Yes.
Yeah, I'm not. I think. I don't know. I'm not stating it quite correctly, but yeah. So that's, if you can go into that more, that'd be awesome. Thanks.
Perhaps that would be best to send him a paper and go through it. One thing I was curious of, I'm still learning a little bit of group theory here. So this, why E6 here instead of E8? Why do you go down to E?
Very interesting. E8 branches as E6, so SU3 into E6. That's the branching of E8 which is useful here. So it's also noticed by string theorists. They did come as far as branching E8 as into SU3 cross E6. This SU3 we interpreted as SU3 space-time. Space-time in the octonionic 8D space-time is mapped as a vector space to SU3, which can then be mapped to 10D space-time, from which we will recover our ordinary space-time. E6 is beautiful. Is the only exceptional Lie group which admits complex representations, which we need to describe fermionic states. Hence, so the Dirac equations symmetry group in 10 dimensions or on an octonionic space is E6. Good that you brought it up. The Dirac equation is actually described by the exceptional Jordan algebra of 3 by 3 matrices, which are Hermitian and have octonionic entries. That's the exceptional Jordan algebra. It's when you complexify it, its symmetry group is E6. So E6 is very closely connected to the Dirac equation for 3 fermion generations in higher dimensions, 10 spacetime or 8 octonionic dimensions. So E6 is at the heart of the particle physics. The E8 helps to bring in spacetime. E8 is spacetime plus elementary particles. Does that help? Does it answer?
I think I see where my theory would fit into this. So I'm kind of looking at it from a partial differential equations perspective, and in order to approach this, I would need to basically have solitonic solutions corresponding to each of the particles from some weird, bizarre nonlinear wave equation. And that sounds a lot harder than doing it this way, but
yeah.
those
So
would be interesting.
this captures that solitonic information in the sense that there are only certain solutions allowed by octonionic space, which can be called elementary particles. So remembering Einstein when he said that particles are singularities of space-time, here what has happened is space-time has become non-commutative and only certain particle solutions are allowed. Maybe you call them solitons. They are our quarks and leptons. We
Yeah,
cannot We cannot put arbitrary elementary particles on the octonionic space.
That makes sense.
So
And in my case, I don't know for sure if I can even map some nonlinear wave equation to this octonian space. Whatever the nonlinearities would have to be, they would have to be, yeah, they would have to generate a set of solitons, so the finite set. So usually when you have these, when you go from a PDE, you're usually getting one solution or infinite solutions. So generating a finite set of solutions would be a strange thing indeed.
Dr. Dr. Singh, could you relate this to the Higgs field, the spin zero, the Higgs field?
Yes, please.
Yes. So when we looked at the particle content of this E8 cross E8 theory, we do find standard model 3 fermion generations. We find standard model gauge bosons. We find 12 new gauge bosons corresponding to pre-gravitation. But we don't find so far any new fermions. But we do find 2 Higgs bosons. One is the standard model Higgs. The other is a charged Higgs. In this theory, the massive standard model Higgs gives masses to left-handed fermions, whereas a charged Higgs gives electric charge to right-handed fermions. The right-handed fermions are mass eigenstates, square root mass eigenstates. The left-handed fermions are charged eigenstates. So there are 2 Higgs.
So that's your secret sauce.
Sorry?
I said that's your secret sauce.
That's my secret. Plus, there is more. The Higgs is very, very unlikely to be fundamental. I don't think there's a spin zero fundamental particle in nature. This theory is suggesting the Higgs is a composite of all the standard model fermions. The things that it gives masses to are the very things of which it is made.
That makes sense.
We are looking into
my approach.
Yeah. Yes, it's just not published. We are still looking into it. But the Lagrangian seems to suggest Higgs is a composite of fermionic pairs. So if they pair with spin half, spin minus half pair would form a spin zero scalar.
And that's not
evidence.
That's non-commutative, so it makes sense.
Right. Okay, so now coming to the constants. Before symmetry breaking, there are no coupling constants. Before symmetry breaking, there are no coupling constants. There is only an overall length scale. The coupling constants like fine structure constant, QCD coupling constant, weak mixing angle, mass ratios only arise after symmetry breaking, because that is what separates the forces. No, coupling constants are meaningful to talk of only when you have forces which are separate and which relate the boson-fermion interaction. None of this is there before the unification is broken. Now, the states of the elementary particles before symmetry breaking are described by octonions. After symmetry breaking, also they are described by the octonions. There is no freedom. The coupling constants are nothing but the relative weights of the left-handed fermions and the right-handed fermions. Symmetry breaking separates fermions into chiral fermions, left-handed, right-handed. Their relative weights of the states, whatever relative amplitudes they get, are determined by the theory, by the algebra of the octonions along with the Lagrangian. Those weights become coupling constants. And whatever will appear in the as the fine structure constant in the Lagrangian, or whatever will appear as mass ratios, are, from the octonionic point of view, just relative weights of states, and they can be just read off from the forms of the octonions after symmetry breaking. That is where these numbers really come from. There's no freedom. There is absolutely no fine-tuning and no freedom. So that's why we have this nice expression for the fine structure constant and for mass ratios, which show reasonably good agreement with the experimental data. There is somewhere difference. We understand why the difference is there, and we are trying to sharpen so like the fine structure constant differs from the measured value by 2 parts in 10 million. It's known accurately to the 11th decimal. We get it correct up to the 6th decimal, but the 7th decimal we have a 2 parts correction, so that's like 2 in 10 million. And mass ratios.
What gives rise to that?
Sorry.
Correct. What gives rise to that correction?
Very good, very good. So we have an explanation in the paper. We worked it out. These numbers coming from theory are in the octonionic space. Our philosophy is that elementary particles, quantum elementary particles, don't live in 4-dimensional space-time. They live in a higher 10-dimensional space-time, but the extra dimensions are very thin. They are not Planck scale thin. Their thickness is of the order of the range of the strong force or the weak force, 10 to the minus 13 centimeter, 10 to the minus 16 centimeter. The theoretically predicted value is in the octonionic space. The measured value is in a 4-dimensional space-time. There will be a correction. We know how to calculate that. The value of the correction depends on the scale of electroweak symmetry breaking. And if that scale is around 157 GeV, we can take care of the correction. So it is basically having to do with theory. Calculation is in 8D, measurement is in 4D. There will be a slight difference.
Yeah, that makes complete sense, because at least approaching it from a wave equation standpoint, your adjustment to the fine structure constant depends on where your electrons kind of stabilize, where that size scale is. Because they're the things that are interacting when you measure the fine structure constant to begin with.
Right.
And like with the neutron spin experiment, my quantum mechanics professor devised this in 1967, but it proves that the spin is not at the scale of the wave or the particle. It's much smaller. Like so that's okay. Thanks.
I had a question. If you could elaborate on the terms inside this derivation in this formula that you have.
What is going on here? That's what you're asking.
Yeah, where does this 9/1024 come
Right.
from? And
if we go back to the form of the Lagrangian in the action principle, I can show it to you. Let's go back to where the action is. Maybe little up, please. Little up. This should do. Equation 8 should do. You see this alpha here, that the Young-Mills coupling constant. It is not exactly the fine structure constant, which is denoted alpha. So I'm sorry for this unfortunate notation. If you multiply alpha by L from the first one with the alpha by L from the second bracket, you get alpha square by L square, and there is a LP square by L square sitting outside. You overall get LP over L to the 4th times the alpha square. So there are these two constants in the parameters in the Lagrangian. LP by L, which is a length scale associated with an octonion describing the elementary particle. And there is a Young-Mills coupling alpha. The fine structure constant is the quantity LP4 by L4 into alpha square, because that is what is coming as a coefficient in the interaction between the photon and the electron. Photons are described by QB, Electrons are described by QF for fermions. So the fine structure constant in this theory is LP 4 by L4 alpha square, or let's say LP by L to the fourth into alpha square. LP by L is the length scale associated with the octonions, which will be determined by the octonionic states themselves, which are described. The electron state is described by octonions, and I can calculate the absolute magnitude of the octonion. That is what will give me LP by L. That is shown to be square root of 3 by 32 raised to the fourth power. That is 9 over 1024. That's the origin. LP by L to the fourth is 9 by 1024. Now comes the question of fixing alpha square. Alpha has to do with how the coupling E root M, which was in some form hidden in the unified theory, how it becomes E for the left sector, root M for the left right sector, and then it can be shown that log of this alpha is equal to 1 over 3 into 1 over 3 minus root 3 by 8. If you go up, yes, log of alpha is this new exponent. So alpha becomes this. Now we can, if you like, I can talk, this alpha squared. Log of alpha is 1 by 3 minus root 3 by 8 into 1/3. And hence alpha is exponent of that. And alpha squared gives me this extra 2. If we can go into where did this log alpha equals 1 by 3 minus root 3 by 8 into 1 by 3 come from? We can discuss that. This is really the relative weights of the left-handed fermions and right-handed fermions. The relative weight of the left-handed fermion is shown to be 1/3 of 1 by 3 minus root 3 by 8. That of the right-handed fermion is actually just the minus of that. So that am I helping you with this?
Yeah, no,
Jeremy?
this is good. It's breaking it. It's helping me understand where this is all coming from and how you derive that. I have to go through this. I have to go through.
It helps to map the math to the specific situation a bit.
Yeah.
It is related. It will involve both the Lagrangian and the octonion algebra. The octonions themselves will not tell the fine structure constant because that's a physical quantity. Physical quantities are fixed by the action principle, by the Lagrangian, by the symmetry breaking. The point is, these quantities in the Lagrangian cannot be free.
Yes.
It's all tightly knit right from the start. The octonion algebra is in command, and it will decide what values L and alpha will take in the. So if all this works properly, all the 26 free parameters of the standard model ought to be getting fixed uniquely just from the algebra of the octonions along with this Lagrangian without any fine tuning. If there's a fine tuning, this theory is wrong. It can be thrown away.
You should definitely. It sounds a lot like some of Professor Unzicker's stuff, but he doesn't have the mathematical background to really elaborate on that. But Professor Unzicker had he was saying that the right direction to go involves quaternions or octonions and some higher order maths. But he has
the name, please. I'm not getting the
idea, not anything specific yet.
Well, but what's the name? Can you spell it?
Unzicker?
Yeah, what was his first name? He has a channel. He's a historian he's a physics historian. So, but he has enough mathematical background. Alexander Unzicker, yes. So he has enough mathematical background that he's pieced together a bunch of interesting stuff.
Okay, I'm sorry, I don't know the name. My ignorance. I'll look him up.
Yeah, he doesn't have a full model or anything yet, but he's going in this similar direction.
Quaternions and octonions, is it?
He was using quaternions for his things, but he's very early in this on that path.
Yeah, so I saw these constants. I should mention in this theory, there are only three fundamental constants: Planck's constant, Planck length, and Planck time. These are there right from the outset in the action principle. Every other constant of nature should come out from these three.
Agreed.
Nothing more will be put. So, like
So-
fine structure constant, E square by H cross C is 1 by 137. So, E square is 1 by 137 of H cross C, and C is Planck length over Planck time. So, electric charge is now known to be a numerical multiple of Planck length, Planck time, and H bar. Similarly, Newton's gravitational constant is already there from the beginning. It can be written in terms of Planck length, Planck time, and speed of light. And sorry, Planck length, Planck time, and H bar.
Dr. Singh, what could you say how this, when you mentioned thermodynamics before, how would this relate to gravitational entropy instead of the entropy of matter?
Well, good question.
Yeah. Right. So, how does classical space-time and classical gravity emerge from these atoms of space-time matter, which are basically fermions with their own bosonic fields? An atom of space-time matter is a fermion with its bosonic field. When many fermions get entangled, for whatever deeper reason, when lots of fermions get entangled, a localization process takes place where the matrix collapses to one of its eigenvalues. Wave function collapse consists of the matrix going to one of its eigenvalues, and that happens as a result of supercritical entanglement. Right here. When there is a lot of entanglement, classicality emerges, and basically, the entropy, say, of a black hole is related to the emergence of the classical black hole from underlying degrees of freedom which are not being observed. So the classical black hole results as a consequence of entanglement of many atoms of space-time matter, and because we are observing the classical system and not its microscopic degrees of freedom, there is entropy. Yeah, right here. Yes.
That makes a lot of sense. I mean, because once we have macroscopic structures, they still appear to be made out of particles to some extent, which it's
Right.
like it's sort of like they're all measuring each other
Yes.
and collapsing their
And
wave
if
function.
we are not observing those particles directly, then we have loss of information, and that is what is the origin of black hole entropy.
Very cool. Thank you.
You're welcome. Thanks for the discussion. So our current goal is to try to derive all the standard model parameters. We at the moment have 10 out of 26. We are working to get the rest. We are hopeful we'll get them all if this theory is correct. And then try to come up with some predictions. These are post-dictions. Try to come up with a clean prediction to test the model. So like I said, there's no smoking gun right now. Nothing like Einstein's bending of light. He predicted that his bending is twice that of the Newtonian value. We don't have something clean like that, but we have results like there will be spin 1 pre-gravitating gauge bosons. The neutrino suspected to be massless, and the reason for flavor oscillations is something else. We can talk about it sometime. There are 3 right-handed sterile neutrinos. There's an additional charged Higgs boson. The gravitational interaction between particles and antiparticles is repulsive. Yeah, so These
I have a question
general
about this. You say that the neutrinos are possibly massless, but some recent physicists have posited that the right-handed neutrinos might possibly account for the dark matter.
right. Maybe should we go along the dark matter path? I'm quite actively looking at it right now with some people in Europe. Just today we had a meeting. Thanks for bringing up dark matter and dark energy. So we could talk separately about the reason in this theory why neutrino oscillations are possible is because there are three right-handed sterile neutrinos, and neutrinos turn out to be what are called space-time triplets in the octonionic space, irrespective of parity. The left-handed as well as the right-handed neutrinos are space-time triplets, which means they can the flavors change by changing directions in the octonionic space. And for that, the channel for changing the direction are the sterile neutrinos. So neutrino flavor oscillations are caused by using sterile neutrinos as a channel instead of using mass as a channel. The standard picture is there are no sterile neutrinos. The active neutrinos have flavor eigenstates and mass eigenstates. We are saying that instead of mass eigenstates, we have three sterile neutrino eigenstates, which are providing the channel for these flavor oscillations. So that's the neutrino story. Now the dark matter story, very closely connected to Milgram's Mond, who has, I think, been in the news recently. Milgram's Mond, as you know, modified Newtonian dynamics says that when accelerations become below certain critical value, the law of gravitation changes from gm by r square to root gm by r multiplied by an acceleration constant. So gravity, instead of falling as 1 by r square, falls as 1 by r if the accelerations become very small, and we have very strong indicators in this octonionic theory that that is what is going to happen. So in a sense, we predict Mond. We predict that near compact objects, general relativity and Newtonian gravity dominate. Far from compact objects, if gravitational field become very weak, then the Mond description of gravity dominates. We see that clearly in the classical limit of our theory. So our current picture is that there's no dark matter, but there is a modification of gravity, which has something very interesting to do with holography. That if you take a volume surrounded by the area of the boundary, we normally think of the gravitational field as the boundary being determined by the total mass inside and locally by its mass density, the Poisson equation. Take the mass inside, divide it by the volume, find the local density, and that's the source for gravity. We find that that is correct, but there's an additional term. Take the square root of the total mass inside. This goes back to the square root masses being important in this theory. Take the square root of the total mass inside this volume divided by the area of the boundary. Square root gm divided by 4 pi r square. This is the source term for Mond. The source term for Newtonian gravity is gm by r cube. That's the density, g times the density. Laplacian phi is 4 pi 0, but now 4 pi 0 plus root m by r square. This is the Mond contribution, which will become important at low accelerations. This ties in also with, if you remember, Verlinde's entropic gravity hypothesis. He's been saying similar things, that Mond is driven by additional contributions. And this also ties with our Yuan grav. you remember, there's a U1G in the theory, the right-handed counterpart of electromagnetism. That is sourced by root M. That's like a fifth force. Mond is really like a fifth force modifying general relativity, whose source is the square root of mass.
Well, I suppose you
And
could look at it that way. There was Mike. Have you heard of Mike McCulloch's research?
Mike?
Mike McCulloch. He was he had this quantized inertia theory, and that also predicted galaxy rotation curves. And
yes.
it supposedly they got some experimental results, and then it went dark. So that's interesting.
This is very similar to Mond.
Yes,
Similar to Mond, but
it makes a lot of the same.
horizon. Yes. Associated with every accelerating object, there is a horizon. If the acceleration is a, the horizon scale is c squared by a, where a is c is the speed of light. Acceleration a, horizon c squared by a. If the acceleration goes very low, the horizon becomes so large as to become comparable to the size of the universe. That is when Mond becomes important, when the low acceleration gives a very high c squared by a Mond-like horizon. Yes, so very beautiful in my opinion.
Dr.
Very
Singh,
elegant.
could you relate that to dark energy then? Because I remember I was reading your paper.
Yes.
Okay, thanks.
Yeah. So if we have area density of square root of mass, root m by r square, and if it has to be consistent with general relativity, it has to be made relativistic. So there has to be an energy momentum tensor component, which is area density. So I call it TIK area. Source is square root mass or square root of the density divided by the area density. In the relativistic limit, this is going to pick up a pressure contribution. Because it becomes a fluid, it's not just have the energy density, which is now the square root mass density, it will have a pressure contribution. The evidence, not published, not fully worked out, suggests that that pressure is actually negative, like in the case of the cosmological constant. It mimics the cosmological constant. So this U1 grav fluid at cosmic scales is mimicking the cosmological constant and hence dark energy. And again, it has a very close connection with the holography and the amount of information stored up to the Hubble radius. So U1 grav at large scales possibly will become dark energy. It's not published, not fully proven yet, but that is where. So U1 grav, the fifth force on outer galactic regions, behaves like Mond and replaces dark matter. On cosmic scales, it behaves like dark energy and replaces the cosmological constant. So we have a universal law of gravitation, which is modified GR by a fifth force, which is sourced by area density of square root mass, so to say. We also call it dark matter without dark matter and dark energy without dark energy, because we are modifying the source term of Einstein. Normally, people are modifying the left-hand side of Einstein equations by adding more gravity. The right-hand side was always the energy momentum tensor. But we are now saying we overlooked something. The right-hand side has a so-called holographic contribution. Mass has an additional contribution coming from square root of mass, which is related to this U1 grav or the fifth force.
Dr. Singh, when you're talking about, when you're talking about, okay, thanks. The fifth force, and you're relating that to dark energy, would that tie to the quantum potential as a, with the square root being a non-commutative frequency?
I mean, the David Bohm kind of quantum potential?
Yeah, but in terms of the non-commutative.
I don't know the answer. I'll have to think about it.
Yeah,
It
because
looks
yeah,
interesting because it is root m by r.
yeah,
There may be some. It is very definitely true that on these large outer galactic scales and cosmic scales, it's as if quantum theory makes a comeback.
yeah.
Very large systems are quantum again. So
Yeah,
holography is a very quantum feature. It's not a classical feature. Its roots are in quantum theory.
yeah.
Near compact objects where accelerations are were sufficiently high, general relativity dominates. That's the classical domain.
Hmm.
But when accelerations go below critical Mond acceleration, and we are on outer galactic regions and on cosmic scales, it seems as if there is a quantum gravitational effect related to holography. So then we should see if this is Bohm's potential. Maybe. I don't know.
Just so you know that Professor Basil J. Hiley, who he collaborated
Yes,
with,
yes.
and he's working on along Cohn's. He's working on a new paper now, but he's totally relying on non-commutativity also
Yeah,
with the
yeah.
Clifford algebras and.
Yeah, one of my former students is very close to Hailey in London. So I
Oh,
do get some news of that this is going on there. I look forward to the paper. Yes.
oh, great.
Yeah. So I think many people, like people working on octonions, Cold Fury, Latham Boyle, and several others, people working on non-commutative geometry, Alan Kohns and group, and many others. Trace dynamics, there are very few people looking right now at Adler's trace. But if you take trace dynamics, Alan Kohns non-commutative geometry, and the octonions, these together seem to give a new hope for unification, which goes beyond quantum theory, which goes beyond real number spacetime manifolds, goes beyond Riemannian geometry to non-commutative geometry. And in certain way, I see this as a new string theory. There's a lot of parallel with string theory, but improvement. String theory works with extended objects. We have also extended objects. We have two brains, but we never compactify the extra dimensions. We define fermions on octonionic space, not on Minkowski spacetime. We use trace dynamics, but not quantum theory. But we still do E8 cross E8, what was very popular in string theory in the 1980s. It didn't work to my understanding because they didn't use octonions as spacetime. They tried to compactify, which gives rise to these billions and billions of vacua. No compactification, please, and go more general than quantum theory to Adler's dynamics. So one way to look at it is that we have basically revised string theory in a sense. We can say we have come from purely quantum foundational directions, but there are so many parallels with string theory and improvement or corrections, so that I would not leave out the string theory analogy completely. So the octonionic theory is in some sense a revision or improvement of string theory.
So, you know that Sir Roger Penrose, he doesn't believe in inflation of the universe, and it sounds like your definition of
Yes,
dark energy is his. He says that what he instead of inflation, he says you just have the cosmological constant as the gravitational potential, and that would be the dark energy. He says that is the dark energy, and that sounds like pretty much what you're saying.
that's
Also,
that's like you and Grab. But one thing I maybe differ from him, before the electroweak symmetry breaking, there is unification. There is no general relativity. There's no standard model. There's the unified force. This unified theory is actually a conformally invariant theory, maybe like his conformal cyclic cosmology, but I need a certain kind of inflation there for things to work. What his point is that, inflation pre-assumes a space-time before inflation. I think that's a very good criticism. In my theory, while there is a octonionic inflation, there is nothing before that. So there is a parallel with this cyclic cosmology in the sense that these atoms of space-time matter are there. They undergo a spontaneous localization, and the so-called Big Bang is the opposite of. So it's like if you took a gas in a box in equilibrium, and suddenly there was a fluctuation and it all went to a corner, it will explode back to fill the whole box and regain entropy. So a Big Bang is the opposite of a spontaneous fluctuation which localize these atoms. So it's not exactly the same as his cyclic cosmology, but it has some similarities with it. So
Yeah,
I would also disagree with standard inflation, but a
mhm.
certain kind of inflation I need.
Okay. Yeah, he was having a debate with Nobel physicist Gerard de Hooft of you
Uh-huh.
know, they were having a debate about Gerard de Hooft uses a Penrose diagram for his eternal black hole, which his eternal black hole sounds more like the atomic space-time model that you're using is term because he relies on the non-commutativity of time and frequency, for the black hole. So that sounds very similar.
Mhm.
Anyway, this is I mean the other thing is the
Yeah.
oh so like well the because Penrose is saying that he relies on the de Broglie Einstein relation to say that mass originates from frequency, and then he's basically saying that all the black hole singularities at the end of the universe, the gravitational entropy reverses, and that's what creates the next universe because you have asymmetric time and you have extremely low gravitational entropy.
Yeah.
Interesting.
So for me, before the left-right symmetry breaking, gravity is actually lost. Space-time is lost long before we reach something like the Big Bang. So I would right now focus on this octonionic inflation, symmetry breaking, emergence of gravitation, emergence of standard model and quantum theory, and try to explain the standard model parameters and this emergence, and only then go to what was the moment of creation like. I would let that wait. That we are dealing with numbers now. You can make predictions for experiments. We can explain standard model constants. So I'd like to get my hands into predictability, because that's one difference from string theory. Because we are working with a closed knit system like the octonions and trace dynamics, no room for freedom, no multiverses, no anthropic principle, we can actually calculate numbers like the mass constant, mass ratio. So we would like to put our attention into calculating the standard model.
On that
And
note,
all the
I got to go soon, but on that note, definitely take a look at squeezed vacuum states. I can send you some references if
yeah,
it's
please.
helpful. But there, I bet if you can make some predictions regarding squeezed vacuum states, I can build you a device to test it. I would love to collaborate.
Lovely. That would be interesting. So you are saying that emergence of classicality should be related somehow to squeeze states, which is of course an idea there when we talk of decoherence. I keep that in mind.
Yes, if you can
Maybe
figure
you
out
could
any
also look
predictions.
into how to look for these supra-quantum correlations. I think that it could be a very clean test to establish that quantum theory is approximate.
Yes, I think so. If
Look,
you go ahead.
if you can do something with squeeze states of photons over there, You entangle two photons and do your Alice-Bob experiments with the entangled photon pairs at sufficiently high energies. Then we expect these supraquantum correlations to show up. To me, that looks like the cleanest possible experiment to test the limitation of quantum theory. And that could be a turning point if that experiment can be done. It's cleaner than many other attempts to test quantum mechanics.
Yes, I have an idea in mind. We can talk about it afterwards, perhaps. But
Sure,
I
sure.
would love to hear what your predictions say as well. Anyway, I should get going shortly. Lovely talking with you. Let's definitely network.
Thank you.
Jeremy, put us in touch.
Thanks
Yes.
for coming. Yes.
Thank you so much for taking the time out. We're going on a little over 2 hours now, so and I think we've covered pretty much everything. So I want to
Yeah,
wrap this up.
yeah.
And if people have additional questions, they can contact you through your website, webpage here on which I will link to in the description below. Do you have anything else that you'd like to share or add or say before we wrap up?
My hope is that I hope and wish the community starts looking at these foundational aspects of unification, namely that we should not be quantizing gravity. It goes against our understanding of quantum theory. Quantum theory cannot quantize gravity the way it quantizes other forces because gravity has to do with space time. You cannot quantize gravity and yet want to have space-time, and quantum theory needs space-time even when it is quantizing gravity, because it needs time. So we have to think in this Adler picture of a pre-quantum, pre-gravitational phase, and the final message is that both gravitation and quantum theory are emergent phenomena, emerging from some underlying more general theory. Now, our goal is to look for that theory. It does not require going to the Planck scale. It can be built at currently accessible energies because of the reasons that we talked about. And that is a deviation from how we are thinking about unification in particle physics. Somehow that turnaround has to happen. I'm saying the reason why we do have 26 free parameters in the standard model is a strong indicator that we don't understand the standard model at even current energies. Something is incomplete in our application of quantum field theory to the standard model already at lower. Otherwise, why do we need 26 free parameters? A good theory would be complete, no free parameters. And that has to do with we must not be using Minkowski spacetime labeled by 4 real numbers in quantum field theory. If we do that, can still do the physics, but we'll get 26 free parameters. The moment we replace these real numbers by underlying non-commutative spacetime geometry, even needed at low energies, those free parameters get fixed. So I like to give this analogy. Suppose that 100 or 150 years ago, people measured specific heats of elements. They find strange numbers, high for some element, low for some other metal, and they say, these are fundamental numbers. They cannot be derived from anywhere. These are like the free parameters of solid state physics, like stuff. But then comes atomic theory. It says, no, these are not free. They are fixed from the properties of atoms. So atomic theory is analogous to describing space-time by octonions. The moment you go to a better description of space-time, standard model parameters are not free, just as specific heats are no longer free if we understand elements and metals in terms of atomic properties. So we have to understand space-time in terms of non-commutative elements like octonions. We have to understand quantum theory as emergent from trace dynamics. If we are able to take those two steps, the standard model gets fixed and gravity also emerges. So I hope the community would see in this things in
Yeah.
this new light.
Are you aware of like Professor Jean Brimont pointing out that Bell's inequality wasn't even understood by Stephen Hawking because, in Bell's inequality, it disproves quantum field theory because they're assuming a symmetric rest frame, but the Bell's inequality, it's debunks that. So I think you're, more, we need, it's, I mean,
Yeah,
because
I would take quantum non-locality as a very serious puzzle. To me, it violates special relativity. I totally agree with Einstein. Quantum non-locality and special relativity do not get along. And because quantum non-locality has been observed, we need to modify special relativity into something like a non-commutative space-time structure. In fact, non-commutative space-times go along with quantum non-locality in a fairly decent way. So the way to resolve the EPR puzzle is to make space-time non-commutative.
I'll just share how I got into this subject was actually from music theory because Alain Khan he has this lecture called Music of the Quantum Sphere, and he points out that if your music theory is actually non-commutative, and he's the only scientist I know who actually reveals the truth of music theory. But if you look at the history of Western science, the real geometric continuum originated from music theory, but they were using the wrong music theory. And like in India, if you go back to the three gunas, the ancient three gunas philosophy, that is actually non-commutative music theory. So I'm just saying,
Yes.
this led me into meditation in terms of like the proto-consciousness concept from Penrose and all that information and the gravitational entropy, dark energy, and all that. So anyway, thanks very much.
Yeah, I agree with you. Even at low energy, space-time is fundamentally non-commutative. Where if the world is quantum, space-time is non-commutative. If space-time is commutative, the world is classical. You cannot have quantum world and space-time commutativity except in an approximation, and this is not the best of approximation. It's the source of our ignorance.
All right. Thank you very much, Dr. Singh.
Thank you. Thank you
Yes.
to all of you.
Thank you so much, and hopefully this interview helps you get a lot more exposure and views from the community. So
Yeah,
this
thank
is
you. So you know Kurt, is it?
Kurt has
You know
yeah.
Kurt?
Yeah, Kurt Jamungal. He's booked up for the next year or so with guests and stuff. But man, I'm gonna definitely send him this and tell him to watch it and check out your work.
Yeah,
Uh,
yeah. I was in touch with him some time ago. Yes, yes.
Awesome. Yeah, I found you through some of the contacts I have through him and my channel. I forget who sent me your paper and stuff, but it was a pleasure to have you on. I learned so much.
Thanks for inviting me. Thanks very much. Yes.
Look at this. I have too many tabs open. I have to go and copy these all as links into the description, which I'll put in the description below for everyone who wants to do more deeper research, because obviously this will keeps people busy for a while.
Okay, great. So I can maybe log out now.
Yes, we are.